Uh, Hello, everyone. Welcome to our talk today. And our title, our presentation is Iceberg Geo Data Type. And we're going to talk about how we can transform geospatial data management at scale through the Iceberg Geo Data Type. And my name is Jia, and I'm from Variables, also Apache Sedona. And this is my friend, Szehon Ho from Databricks. So as you guys already know, so geospatial data is becoming more and more important from logistics to urban planning. And also, meanwhile, so the amount of available geospatial data grows exponentially in the past decade, thanks to the availability of GPS devices, satellite images, all this data, they're all geospatial data. However, processing this kind of geospatial data efficiently at scale give us very unique challenges, and that's how we solve that through the Iceberg Geo Data Type. So here is the agenda today. So we're going to first go through the origins of Iceberg Geo Data Type, and then my friend Szehon going to talk about the details of the Iceberg Geo Data Type design. There are going to be lots of me there. And finally, we're going to have a demo about the Iceberg Geo Data Type, basically how that looks like once it is finally merged into the Iceberg stack, Iceberg implementation. Cool. Start with the origins. So what do we use before the Iceberg Geo Data Type or even Parquet, right? So in the Geo community, so we are really good at reinventing the wheel. So before that, so we have all sorts of different geospatial data types, right? So there is text files with WKT encoding. So WKT means well-known text. There is also WKB encoding. There is also shape files, GeoJSON, and the geo package, right? So there are so many of them. In fact, there are even more than 80 different geo file formats. And they are great formats, and they have their strengths and like pros and cons, right? But the problem is that all this type, so when it comes to cloud environment, cloud storage, and big data, right? They show suboptimal performance. And another problem is all these formats, they put the geospatial data into data silos because they don't work with the non-spatial data. They don't work with other formats people use for regular data. So that creates lots of troubles. Because of that, the geo community started to look for options that can work with cloud natively and also work with other non-spatial data that enable us to exchange and share geospatial data at scale. So the community started an effort called GeoParquet in 2022, and we made a spec out in late 2022. And in this GeoParquet, essentially what it does is it tries to define the geo data type in Parquet, and also the geo encoding and stats. And all that, Szehon going to talk about that later today, right? But the problem is that, so this GeoParquet file format, it is actually an extension of Parquet. It didn't add the native type into Parquet itself. But of course, that already gained lots of traction in the community. So there are many vendors start to support GeoParquet. There is GeoPandas, Apache Sedona, and Google BigQuery. They all adopted GeoParquet format. And now the question is, so okay, Parquet has sort of geo support, right? So what about Iceberg? So how can we leverage the power of Iceberg to support data lakes, to support transactions, all this cool stuff, right? So given that, actually, the interest of supporting geo in Iceberg actually is increasing in the past few years. So the first ticket about supporting geo in Iceberg was created in actually 2021, and in around 2023, so there is a GeoLake project that creates a research prototype adding geo to Iceberg. And in late 2023, there is Havasu from my company, Variables. It actually created a geospatial support in a fork of Iceberg. And we put it into production. And due to all this effort, so the community, the Iceberg community and the geo community obviously started the discussion about how can we add geo type into Iceberg as a native data type. We started this discussion in early 2024, and after a year, very, very long time, okay, so finally it got merged in February 2025, and my friend Szehon going to explain why this took so much time. Okay. All right. So now, Szehon, take over, please.
Sure. Oops. All right. Thank you, Jia, for the introduction. So I'm Szehon. I'm an Iceberg PMC member, and for context, I was the one who first started looking at geotype in Iceberg, and I'll explain why it took so long. So basically, I think really what took so long was, from Iceberg point of view, we just don't have any knowledge, domain knowledge of geotype as much as Professor Jia. For example, definitely we saw on the Iceberg mailing list people from GeoParquet, GeoLake, Havasu talking about it, but we couldn't, at the time I had no idea what these projects were doing. And they were also talking about very technical things, WKB, WKD, different partitioning strategies, Google S2, Uber H3, Microsoft Bing Tiles, geofiltering. And it was just kind of overwhelming, and we didn't have, I think, the confidence to say we can do a good job to add geo to Iceberg. But I think what convinced me that this was a good use of my time, I think one time Jia flew down from Seattle and we met for coffee, and I asked Jia, like, oh, why do you want to contribute geo to Iceberg? And he said their users don't want the data to be locked in. They want their data to be in an open geo format. And to me, that struck as like very core to the central goal of Iceberg, to be a common table format for a different analytic engine. So that made me think, okay, this is probably going to be a long journey, but it's probably worth the time because geodata fits very well into the scope of Iceberg. So, engineering, first principles, there's a lot of complexity. We have no idea how partitioning anything is going to work. So let's just say, what's the minimum we can do to make progress? And that's just going to be what's defining a type. And that, in the end, took a year, but we defined type. so why we define a type, right? So as Jia mentioned, standardization is a big one. Obviously, you can store geodata in Iceberg today, but if you don't have a standard, only your engine can understand it. No other engine will know what this data means. And also, Iceberg, we can do filter pushdown if we understand the data, right? Iceberg has the ability to prune out files that don't match a query filter, and if we understand the data, we can do a much better job at that. So if you ever want to add a type in Iceberg, there's two main things to do. The first is at the file format level. Iceberg sits on top of file formats, ORC, Parquet, Avro. So simply, we need to define how to encode it in the file format. Second thing, Iceberg has metadata on top for filter pushdown. We keep track of min-max bounds for each file. And so we need to define what does min-max bound mean for geo. So simple, two main things. Encoding geo. So first, okay, I have to actually go back and see what is geo. I don't really know. Fortunately, geo is pretty easy to pick up for me. You can see geodata like on a map, so I think that to me was really easy to pick up. In Google Maps, you can make geodata very easy. You click once on the Google map, you get a point, which is coordinates. You click another time, you can get a line between points, and a few lines make a polygon, and then you have like different collections of any of these, right? So geodata is pretty easy to know what it is. And fortunately, it's always great if there's already industry standard ahead of you, and that's the OGC. They're called Open Geospatial Consortium. And fortunately, they already define like a class hierarchy for what is geodata. So we don't have to define geodata. That's great. And fortunately, they also the same body made a specification how to encode to binary, which they creatively named well-known binary, WKB. And there's also a WKT, which is for text, which I think Jia will use later in the demo. But for us, when we encode the file format, we'll use binary. So we just take their specification and encode to binary. And their specification is pretty simple. Their first bit is by order, then some bits representing one of those classes I showed earlier, and then a class-specific encoding. So halfway done. Okay, bounds. Iceberg keeps track of lower and upper bounds for geo. So what does that mean for geo? Going back to visualization, the main bounds exist in geo mainly in the form of something called bounding box, where you physically draw a box to cover all the geo data in your data set. Again, it's very easy to see on the right, I have like a bounding box around geo data of all 50 American states. So that's great. There's no confusion there. And the good thing about a box or even a cube, you can define it by 2 points, right? There's like a min point, which is x min, y min, potentially z min, and then max point, which is x max, y max, potentially z max. And that maps very well to Iceberg that you have one lower point and one upper point. And the only kind of iteration here was, I think Ryan Blue made a nice observation. Initially, we were thinking to use WKB to encode the bounds in Iceberg metadata, but Ryan Blue made a nice observation that Iceberg, we want to have very compact metadata because it's very critical for query performance and writes. And so we actually have a custom, because we know it's always a point, we can skip a few bits, and apparently that kind of adds up over time. So we have a custom encoding for Iceberg metadata for bounds, which we just concatenate the values directly. Cool, so in theory we should be done. So why it didn't work? So one thing is we don't have the type in Parquet. As John mentioned, there's GeoParquet, but Iceberg doesn't depend on GeoParquet. Iceberg depends on vanilla Parquet. And the same argument, the same pitfalls happen if Parquet doesn't have the type. First, standardization, we write our geodata to Parquet, but readers and writers outside Iceberg don't know what this data means. And Parquet itself needs to do filter pushdown, right? Iceberg does filter pushdown at the file level, Parquet does it at the row group level. So if Parquet doesn't have geotype, you lost half the battle. And you actually lose even more of the battle because a lot of code paths just copy the Parquet lower and upper bounds into Iceberg. So actually, even Iceberg can't do filter pushdown if Parquet does not have a native geotype. So initially, we were like, oh man, this is like, we don't know anyone for Parquet community. But fortunately, the power of community, when we put the proposal out, one Parquet PMC called Gang Wu reached out and said, oh, I'm interested to put this in Parquet as well. And we were really excited, and we kind of went lockstep and made sure the same proposal landed in Parquet and Iceberg, defining geotypes the same way in terms of encoding and statistics. So that was really, really cool. And I think what was even cooler was the GeoParquet community, as John mentioned. They were kind of building a standard on top of Parquet. They were willing to kind of cooperate for the first time with Parquet community and just say that their next version of GeoParquet would just be native Parquet support for Geo. So that was a really good community effort all around. Okay, so a lot of happy stuff, but there was still many months of kind of frustration. And I think, so here we actually realized we can't escape the weeds of knowing more about Geo than we wanted to. So the thing is, for other types in Iceberg, integers, there's no argument what 1, 2, 3 means. But for Geo, it's not the same. There's a lot of different ways people generate geodata and then different interpretations of the same data. We can't be just like a dumb storage system that initially we were thinking, okay, we just store the data, return the same data, but there was one Iceberg sync, I remember one gentleman told me, if you get this wrong, people will die. Because they said, actually, like, one system writes a coordinate this way, he actually means this point, but then if a system reads it and it means another point, then maybe a bomb goes off in another location, something like that. And no, this has really happened in the Iceberg sync. So okay, so we have to annotate, make sure we have enough metadata about the data so that people know exactly what they mean. So that was the main challenge for us. So it boils down to two main things. One is defining, remember for Geo, a point. What does a point mean on the physical Earth? And then secondly, edge. How does edge mean on the physical Earth? So we have two type parameters. The first one, fortunately, is kind of a known problem in the Geo domain. I think that's a big subdomain in Geo called coordinate reference system. At the very, very high level, I think it's just a means of, first you define a coordinate system on a plane, you estimate the Earth's shape is an ellipsoid or sphere, and then you project that onto your coordinate plane. And that's a well-researched topic. CRSs are already specified, so we just need the user to specify the CRS they use to generate the data. But there was some bad news. There was a lot of debate there about what's the good way to specify it. So, our friends at OGC, they had one way, which is they had a database of all known SRID or CRSs. And then there were some people saying, oh, what if I want a custom one? Then I want the ability to have a JSON representing that. And people were debating, is that really a standard? So that kind of went on for a while. But the saving grace was Iceberg as a table format, we don't want to be opinionated. We just want to support what majority of people want to use, but we have to make sure they're specific in specifying what they used. And so we have CRS as type parameter, and we support both SRD and ProJSON as CRS parameters. And then a note is, again, we have to understand the data in order to do filter pushdown. So Iceberg implementation will do filter pushdown if it's for a geometry column with a CRS that we understand. So that's the first part. And then the second thing that took a long time was the second. So remember, points, edge. Edge also took a long time to get right. So you would think an edge is just defined by 2 points and it's a line between the edge. Between the 2 points. Dimitro from Snowflake had a very nice diagram, so I'm just stealing it here, that is not true. So on the right side, you see a line between San Francisco and Berlin is a straight line. That's called Cartesian edge. But in the real world, if you ever take a flight to Europe, it actually goes kind of across Arctic Circle through Greenland, Iceland, and goes to Europe. It's because the Earth is actually round, right? So, so that's called spherical edge. And again, there's good news and bad news. Good news is there's already commercial, or like a lot of databases that already know this problem. So they implemented two types, geography and geometry type, to capture the difference. But the bad news was there's a lot of debate, again, on the Iceberg PR. Like people were criticizing even the Postgres one, like, oh, that's not real geodesic. And it got very mathematical, the debates. But again, fortunately for Iceberg, we don't care that much. We're unopinionated. We just need to be able to make sure people can specify what they mean. So Menelaus from Databricks came up with a nice list of known and used edge interpolation algorithms that now you can also specify to make sure that you exactly specify how you generated your data. And same thing, Iceberg implementation will only do filter pushdown if we understand the edge algorithm. One note here is the bounds actually have to take the edge into account. If your data set is, for example, the edge between San Francisco and Berlin, your upper bound is actually going to be more than the max and min latitude of both cities. It actually has to go even further north. So that's something in the spec. So yeah, that's why Jia, it took so long. No, now we have two types, geometry type and geography type in Iceberg v3. And from a user point of view, most use case I think is fine with geometry type. You know, the straight edge is actually good approximation for most things, most kind of geodata, especially at the local level, like city or county. If you want to do a more global scale edges, like for example, you're tracking aviation data or shipping lanes, then you want to do geography type. And yeah, that will be some performance hit because, you know, computers take a little longer to calculate spherical edges than straight lines. But yeah, at the end of the day, I'm really happy to get this. This is one of the biggest projects I think I've driven in Iceberg. Just the PR itself, the spec PR, there was over almost 250 comments on Iceberg side, over 400 comments on Parquet side. Even though the lines of code change in spec was not very much, so behind every line of code in Iceberg spec, there's hours and hours of discussion. And yeah, it was really cool actually to work with people from so many different open source communities. Obviously Parquet, Iceberg, but also GeoParquet, GeoLake, and people from different, even competing companies, Whereabouts, Databricks, Snowflake, Apple, Shang, and like many other companies sitting in the same room to decide what's a good standard. I think that was a really cool experience for me. And it shows kind of the principle of Iceberg to be kind of a open, common table format. And what's a table format if you don't have the users who are happy with it, right? So even though it took a long time, a lot of times we want to give up, like, oh, like maybe we can't support Parquet, we can't support geography. At the end, I'm happy we reached a consensus, and hopefully this kind of can change, do a lot of cool things for the geo industry. So I'm gonna hand it back to Jia to talk about what we can do now with the geotypes.
Yeah. All right, thanks for the nice summary from Szehon. Now, that was lots of meat, right? Now this is the fun time. So I'm gonna give you some demos. So this demo is built on top of a couple PRs that is ongoing. So we created a couple PRs on Iceberg repository as well as Parquet to add the geospatial geometry, geography data type, as well as spatial expressions to Iceberg core and the API, as well as the Iceberg Spark Sedona reader. So this is still ongoing. So there might be some changes, but what I'm going to show you next is the sort of like prototype, that how it looks like right now. All right. So yeah. So let's first create a Iceberg table, right? So the syntax here, I'm using like Iceberg Spark together with Apache Sedona. So probably already familiar with this. So this is Iceberg table that has two columns. So the first column is ID. It has a string type. Second column is geometry. It has the geometry data type. And in the table properties, we explicitly set the format version to be v3 because this is a v3 feature. Now we created this table. Let's append some data. So we are appending two records in this table through one transaction, one operation. So record A and B. So each of these records also come with a spatial object, which is a line string object. So a line string object is essentially a line segment defined by two endpoints. Now let's insert those into the table. Let's add more data to the table, right? Let's do two more operations. So in the second operation, we insert two records, C and D. In the third operation, two more records, E and F. Okay, guess how many records we have so far? 6, right? We did that through 3 append operations or 3 transactions, right? And that gave us 6 records in the table. So if we visualize all the records in the table on a map, so that's going to look like this, right? So essentially, each line string is like line segments defined by 2 points. We have A, B, C, D, E, F. Now, let's delete some records, right? So let's assume we want to delete all the line string objects that intersects across the orange polygon here. So in this case, there is B and C that they intersect with the polygon, and we actually want to delete that. So how could we do that with the Iceberg Geo data type? So here is a sentence we're going to want to use. So there is delete from, and there is also vir clause. So in particularly, so there in this vir clause, we use this spatial predicate called st clauses. So st clauses is a standard predicate from the spatial SQL standard. So what it does is it returns true if A crosses B, right? So in this case, the A is the geometry column, which are line strings, and the B is a polygon, is the orange polygon. As you can see here, the orange polygon right here, right now, it is in a text string. And we actually decode that, use something called stgeom from WKT. So that string is actually in a format called WKT, well-known text. And in order to make it a real geospatial object, you're going to use something like stgeom from WKT to create a geometry object. But long story short, you get this sentence, and you send it to Iceberg, and you get the output like this one, A, D, E, F, right? Because B and C, they intersect with the polygon, and we get rid of them. Cool. So how many operations we did so far? So we did 4 transactions, right? 4 operations, so 3 append and 1 deletion. And the table now has 4 versions. So V0, V1, V2, and V3. Great. We can also leverage the power of Iceberg to see the, the commits, the snapshots, right? And also, of course, the type of the operation here. As you see, so if you query the snapshots of this Iceberg table, you'll see there are 4 snapshots, and that they're committed at different timestamp and their types. And of course, you can do time travel to different versions. These are all standard Iceberg operations. As you can see, they are all working great with the native geospatial data type. So you can jump to the snapshot that is right before the deletion. So that has A, B, C, D, E, F, 6 records in total, right? And you can also jump to the snapshot that is right after the initial append. So that gives you 2 records, A and B. Pretty cool. All right. Now let's see something that is a little bit more complicated. Observed with merge. So we have a table like this one. So this is a table we have after the 4 operations, right? It has A, D, E, F, 4 records. That's our target table. We have a source table, so that has 3 records, ID, D, E, and Z. But here is the catch. Look at the 3 records here. So the first one, the one that starts with D, so the line string is actually identical to the one that is in the target table. So that's a duplicate. So the one that has ID E, so this line string is actually different from the one that is in the target table. So that means this geometry actually gets updated. So the third record in the source table starts with Z, right? So this is a brand new record. You want to insert that into a target table. So how could you do that? So you can do that in this SQL sentence. You use merge into. You merge the source into a target on the condition. So the condition is target ID equals to the source ID. So when the ID matched, you want to update the record, update geometry record. And when it is not matched, you want to insert the record from source table into a target table. So after this transaction, so what you got is a table like this one on the right-hand side. So A, D, E, Z, F. So as you see here, we didn't insert any duplicate records here, and also the geometry value of the record E successfully gets updated, and we also have new record Z get inserted into this table. Great. Now, another cool thing about this is you can also do spatial schema enforcement, right? So you have a table like with what we had before, 2 columns, string type and geometry type. Now you want to append a new table that has 3 columns. That means the schema does not match, right? If you just do that directly, it will tell you, okay, schema does not match. Great. Now, if you want to actually really insert this, append that one into that the original table, you could do spatial schema evolution. So what you're going to do is you're going to first alter the original table to make sure it has it is identical to the new schema you want to new data you want to insert, right? So basically, we want to add one more column here that has 3 columns, which is identical to the one you want to append. Now, then you can perform append operations into that table. As you see here, you can successfully merge these 2 tables together, and for the old records that were in the table, because they don't have the value for the num, right? So it has null values for that column. Cool. All right. So now let's look at another funny application here, which is a filter query, right? As you know, filter pushdown is a really important part for Iceberg, for Parquet, right? So now let's look at this example on the left. So as you see here, so there are a whole bunch of points here, right? So the colors of those points indicates the location of those points. So basically, for example, all the red color points, they are in the same Parquet file. All the red color points in the same Parquet file. All the green color points in the same Parquet file. So thanks to the lower bound and upper bound introduced in Iceberg geometry tab, Geo tab, right? You'll be able to create lower bound or bounding boxes in the manifest file in Iceberg. So basically, you have bbox1 that covers the spatial extent of those blue points, bbox2, bbox3, so on and so forth, right? So this gives you the power to perform spatial filter pushdown really efficiently. You can skip lots of irrelevant data. Now let's look at a query. So suppose we have a query, so that is marked as the filter area, right? We want to return all the points that fall inside this filter area. As you can see from the map here, it is pretty obvious. So you're going to return all the points that is within the bbox2. Now let's see how we can do that. So here is the query you're going to run. You're going to use select from where, right? So in the where clause, you're going to put a special predicate called st_intersects. Similar to st crosses, the one I showed you before. So st_intersects is a spatial predicate from the spatial SQL standard. So what it does is it returns true if A intersects B. So in this case, the A is a geometry column, which has those points, and the second one, B, is the polygon. Again, so the polygon were originally encoded in the WKT string, and we use a function called stgeom from WKT to decode that one to a geometry object. So you can do that on the Iceberg table, and you get 3 records. So those are the record points, E, F, G. So if you actually print out the curve plan here, so again, see that we are using Spark and Sedona here. So you can see here, at the very bottom of the curve plan, or the beginning of the curve plan, right? It is a scan. But in this scan, it has a filter, st_intersects. So that indicates that you pretty much filter push down the spatial predicate and leverage the bounding box to speed up the query. Cool. Another important topic for this is, as you already know, for any kind of filtering query in Iceberg, in Parquet, right? So clustering indexing can give you, can create significant affect the query performance, right? So it's the same applies to geospatial data as well. So if we can rewrite the geospatial data or rewrite the files based on their spatial proximity. So that can actually give us much tighter lower bound and upper bound. And that eventually give us very high selectivity, meaning that you can, when you do filter push down, you can pretty much skip most of the data that is irrelevant to the query. So we plan to also add this function to our Iceberg Geo implementation. So we call it Hilbert curve function. So what it does is it's going to take the centroid of the geospatial values. So if that's a polygon, right, we're going to take the centroid. If that's a point, we're going to, of course, take the point itself. After getting all those centroids, we're going to apply the space filling curve, like Hilbert curve, on those coordinates ID x and y. And eventually, we're going to order the data based on that. So that gives you a much tighter lower bound, upper bound, and leads to better performance. All right, I think that's all I have today. So happy to take any questions.
I've been in the geospatial space myself for about on and off for 30 years. So I'm glad to see this moving into Iceberg. The question to you is how many compute engines are really supporting the new spec, and also are they supporting things like the coordinate transforms, like ST transforms and stuff, because those are some of the harder problems to solve.
Yeah, exactly. So yeah, I can take some of this. Yeah, so that's a great question, right? So I think one of the reasons why this spec change took so much time is that so these engines, they all have different behavior, right? There's no unified behavior among this engine about, okay, how should I do ST transform, right? How should I treat the edges, right? So honestly, I would say, so this is a good starting point, right? Because we already defined standard, but it is actually really up to the engine. The engines need to pick up. This is starting point. The engine could follow standard, try to sort of unify the behavior, right? That's our hope. But on the other hand, I think one good thing about the spec here is that we, in addition to the regular single tab for geo, so we actually introduced two types, geometry and geography. So I think most of the engines at least support one of the data tab, right? So as long as you support one, at least you can work with the Iceberg type for now. Of course, there are compromises, right? It is not perfect, but I think that's a good starting point.
Has anybody in the Trino space been talking about trying to support the new Iceberg Geo, or no?
Yeah, I think the Trino folks has been involved in this, and the Snowflake folks and the Databricks, right? So Sedona is also working with the open source Spark, so we are also adding the support there. Yeah.
Trino's missing a hell of a lot of ST calls, right? It's not a complete engine for geospatial.
Yeah, honestly, yeah, that's unfortunately the truth, right? So for geospatial data, the support is incomplete in most of the engines, since it requires lots of expertise, domain knowledge. Yeah.
Yeah, but I think this spec is, I guess it won't really talk too much about the transform, except the ones that push down. So I think, yeah, the good thing is once we have the spec, people can build different engine, can build different expressions. They're not blocked by this spec anymore. I guess that's kind of a separate problem. This is just the storage side of things.
No, I get it. You had to first have the geospatial formats first, right? You can't be walking Parquet files and trying to pull us across and do your geospatial, your point and polygon calls against some unknown source in Parquet. I mean, I get it. So this is a. What about better indexing too as well? Something like I don't know, Lucene indexing for the Iceberg, the geospatial data. I'm not sure what indexing that you started adding into the Iceberg specs.
You mean in general or for geo?
In general.
Indexing in Iceberg. Yeah, I don't know. Anton, do you want to?
Yeah, like if you can partition the world into different sections, then each section can have like a particular position or ID. So you can have like a bitmap. I think Google does something similar. So we were talking about whether we can add the notion for that. So like you would have some sort of bitmap based indexing for geospatial data, but now like for now it's just the min-max values. There would be some changes in like in V4 that would make this. Right now, min-max values, like the skipping only was in partitions. There are some talks about like pushing those min-max values as one level above, so it actually exists in the manifest list. But overall, that's all I personally know about. What's your take on it? Because you're an expert. Anything that you want in particular from Iceberg when it comes to indexing?
Well, the problem is your min-max bounding boxes is only like 100-year-old technology, right? There's a lot better approaches to be able to skipping the content, to be able to pull the so there's a lot of missing. I used to work at NASA and USGS years and years and years ago before geospatial was really popular. So like I said, I've been working on and off. There's a lot of missing pieces. I mainly use Trino now, and it's missing a lot of specs. And in the financial world, commodities data is like corn, oil, all those are location relevant. So that's why geospatial is important, especially in the commodities world where you're talking about, physical assets.
Yeah, I think one key thing here is for Iceberg Delta Lake, this kind of data lake file format. So their intention is not to support some sort of hierarchical complicated tree structure for primary index. Otherwise, you guys already support B+ tree, right, long time ago, right? So I think the purpose here is slightly different, right? So that means for Iceberg Geo in the long term, so we probably won't support like R tree, quad tree, this kind of hierarchical complicated tree structure, right? That probably create lots of storage overhead, and there are lots of other considerations here. So I think for Iceberg Delta Lake, this kind of format, we are looking at sort of relatively lightweight index structures, min-max bounding boxes, as well as Bloom filter, right, which is quite lightweight as a secondary indices.
Yeah, that's what I was hinting at.
Thank you. Great session. Thank you both. One question that comes to mind, especially given how new this inclusion is of geodata in Iceberg. I would urge, and maybe this is already under consideration by the PMC, but I would urge schema evolution and schema bridging standardization early on to enable different compute engines to use what is relevant for them for predicate push down and potentially indexing as well, where things may not quite easily translate over from one compute engine to the other. So having that support would enable a bridge across hybrid workloads, which is typically the case in most enterprises from what I see.
Yeah, I think so. There's different aspects. I think like trying to change a type after data is already in is typically kind of like very difficult in Iceberg, especially like if you already define all these like geo parameters, because data is already written in one like interpretation, and then like if you change the schema, you can change that type on the fly, then you kind of break existing data. But I don't know if that's what you meant, or you meant like in general.
I meant more on the lines of having a different representation for the same logical type that works with different compute engines. So you could have the notion of a box defined in a certain way. It's actually a very trivial example, but so something to the effect that enables a compute engine to function correctly with some added attributes and aspects, which is a similar case in point is data in databases that goes through precision, for example.
Mm-hmm.
So different levels of precision could be one aspect for this data.
Yeah. Do you have thoughts on this?
Do you mean like even in the same column, so the data could be in different, say, coordinate systems? Is this what you mean?
Yeah, I'm sorry, I didn't mean to hijack this, but just to give an example, if you define that you can expand the range of a type to a certain, geometry or dimension, that's within the bounds of coercive conversion between, a system that will store it in one form versus another. I don't know if this makes sense, but I just thought.
Yeah, to me, I think like the OGC defined precision as like a double for all the points, so I think that's pretty standard. I think the one thing that this could take into account is like the partitioning scheme. Later, when we get into partitioning, we'll have different granularities of the partitioning, like you can partition by 3 or 8 or something like that. And at that time, we would have to think about like how we can like evolve the partitioning to be more fine-grained. Maybe that's a little bit what.
No, that makes sense. Thanks.
I think Xiang had one.
Thanks. I wonder if there's a plan to support different partition transform on the geography type and the geometry type.
Yeah, there's plan, I think. So yeah, that's like another talk, I think. But yeah, there's a different. Yeah, going back to Arvin's question, I think like the problem with the partitioning strategy so far, as you know, right? Like Iceberg doesn't support one object mapping to multiple partitions, would you have a lot of that in geo data, right? Because it falls between the partition boundary, and so I guess. Yeah, like I mean, yeah, their research I think was more on XZ2, as you know, like doing that. But yeah, I think we wanted to get the V3 spec out, and so we want to kind of save that for another day, because that's going to be another, I think maybe another year. So we want to have something. Yeah, thank you.
Hello.
Hi.
Good. So actually curious about, is there any plan to introduce any kind of index or encoder or statistic, that can be used for, optimizer or efficient query execution in current normal or geo?
Yeah, so I'm not sure what kind of statistic you are looking at, right? So there, of course, for non-spatial data, I think in Iceberg there is like a number of distinct values, right? You can use that for cardinality estimation. Right. For geospatial data, like those of course can apply to geospatial data as well, right? But I think for geospatial data, if like there are other statistics could be added into the in there, like the average area of those objects, like average length of those areas, right? So those geometries, those could be added, but we need to have like sort of clear use case, right? So like the engine will be able to leverage that, then we could add.
Yeah, it's another year.
Yeah. Yeah. And another thing is the bitmap index, right? So bitmap index, what's the name? Bloom filter, right? So Bloom filter index, unfortunately, I don't think it works with the geospatial data, because I think for Bloom filter it works with equality check, like existence check. But for most of spatial query, as I just showed you guys, it is like range query. It is always a window, right? So that won't work with Bloom filter. So we need to figure out something else, probably some new research, yeah, for that.
A follow-up question. So do you mean in this area it is just the research is still ongoing, and we didn't have a very mature solution at this moment?
So for secondary index in geospatial, so there were lots of research, right? So I personally did lots of research. I was a university professor before. I did lots of research on that, and we are looking at if we can bring some of the research we had before into Iceberg as the secondary index for spatial. But I think that will take time.
Thank you.
Yeah.
Not familiar with this geotype, but is there any performance comparison both read and write compared to other primitive type or complex type like map or array?
Like when you say performance, you are looking at like filter pushdown performance, or what exactly? Or like
both read or write. Both read and write.
So we didn't have. So I think for the benchmark we did before, we did a couple of things. So we in the prototype we had, so we test the compression rate with this WKP encoding together with parquet compression, right? So it has alright compression, right? Of course, you can do better if you have like sort of columnar encoding format for geometry, right? That's one thing. And another thing we did was we studied the performance of the filter pushdown, the impact of filter pushdown on spatial query. That is pretty significant, just as what you could already experience with other primitive type in Iceberg. That is like orders of magnitude faster with proper tighter B-box bound for spatial query. That is super, super important. But in terms of ingestion rate, or like that one we didn't matter because we just, yeah, didn't matter that. Yeah.
Thank you very much. Make sure you rate them in the app. Give your rating for this. The next session will be starting in about 13 minutes.